Programming Throwdown, episode 105, a chatbot with a brain with Peter Voss. Take it away, Jason.
Hey, everybody. So, I think this is going to be an amazing episode. I think, a lot of people are amazed when they work with chatbots. So either you call them on the phone and you get that automatic response, or, even just, having putting a search query into Google in a way is a very kind of short form chat. And so this idea of like this human computer interaction is something that's really taken off. I mean, so many people have Alexa in their home, right? And so, I'm super excited about this area. And we have Peter Voss here, who's the founder and CEO of igo.ai. And we're going to just dive really deep into this topic, how this actually works, cover, a lot of different sort of areas here. And so thank you so much for coming on the show, Peter.
Yeah, thanks for having me.
Cool. How are you surviving with COVID and everything else? Like, how are you dealing with the quarantine?
It's actually worked surprisingly well for our company. We used to work in a very small office crammed together and do a lot of brainstorming. And now everybody's working remote, and I thought it would really be very detrimental. And we somehow managed to adapt. So I've got an awesome team, and so far so good. We still miss some of this close collaboration brainstorming, and I think we're missing out on some of that. So hopefully we'll be able to get back to that.
Yeah. Have you tried any of these whiteboarding, like collaborative whiteboarding apps?
We've tried some over the months, but nothing. I don't think we have quite figured out how to get the same dynamic as people sitting around a table.
Yep. Yeah, we've had the same experience where we've tried a few of them. There's actually a physical one that Microsoft sells, or maybe it's Google, I don't remember. But there's a physical board where you write and as people write, it shows up. Yeah.
Like hugely expensive. Yeah.
Yeah, it's insanely expensive, and there's delay. So some people who are listening to the show probably can't see this, but in this case, I'm in my house. Patrick's on a spaceship. You can imagine the kind of delay that's going to have. So many light years. But you feel it, when you're working with your team and you write something or you see someone write something delayed. It's kind of this uncanny valley where it almost would be better if it just had an artificial delay. It wasn't just kind of always following you a little bit behind.
Anyway, it is what it is. So we'll have to kind of just live with that. But we're doing okay. So.
Cool. So igo.ai focuses on conversational assistants. And so how does this work? Do you is it kind of like a single assistant that you build that many people use, or do you have custom assistants for different consumers?
Yeah. So our product is actually now in sort of second major generation. We launched the first generation actually in 2008, 12 years ago. And there we focused on automating call center calls intelligently. Everybody hates calling into a call center and having a robot, press 1 for this, or doesn't understand you. So that's the market. We basically, these things are called IVRs, interactive voice response. And basically what we're offering in a company called Smart Action is an IVR with a brain. So it remembers what you said earlier in the conversation. It has deeper parsing, deeper understanding, has some reasoning ability, and so on. So they're much better conversations. That was our first generation, focusing on automating call centers. The second generation with igo AI, we just launched commercially last year. Here we're focusing actually on chat channels initially. Because there's huge demand. That's the biggest sort of growth area in customer interaction. And we are focusing on enterprise applications right now. So, large companies that want to give hyper-personalized customer support. But we're also targeting things like a personal assistant for somebody who wants to manage their diabetes, for example. For coaching, we're working with a company that does VR coaching. and they basically need an intelligence engine to simulate the conversation that you're having. So there are many different applications, but right now our focus is on enterprise, working with large enterprise companies. Getting into consumer market, we'd obviously love to have our product available to the consumer, but it's just very hard to break into that market. It's very, very expensive, very risky. So we choosing to first do, commercial applications.
Yeah, that makes sense. And so how I imagine this, and tell me if I missed the mark here, but so you go on, let's say Amazon. Actually, we did this the other day where we had to return something to Amazon, and it was a bit of a complicated return. And so they said, would you like to chat to, customer service representative? And so we did, and we had this quick, chat within the Amazon website. And then they were able to sort of sort it out for us, right? And so this is kind of the market where you say, someone says they're going to chat with a person on a website, but it's actually this bot. And then at some point, maybe it hands off to a person if it needs to.
That's exactly it. And we're taking that whole experience to another level because the current chatbot technology just has severe limitations for doing things like that. And I think we'll talk at length about what those are and why they are. But yes, that's exactly the kind of applications we have. And moreover, we look for applications that are hyper-personalized to the individual. Now, what I mean by that is it's more likely that they actually repeat engagement so that you can also build on the loyalty of the customer, or it's like, as I said, diabetes management where you'd actually be using it every day. But it could also be, your bank or a company that Amazon would be a good example that you may be interacting with on a regular basis, and it gets to know you. And it's hyper-personalized to you as an individual, not as a statistic of a demographic group, but it remembers what conversations you've had and takes that into account. It uses that as context. What you said earlier, what you said last week, what kind of interactions you've had before, and that can be omni-channel as well. That our conversational AI can take into account other interactions you've had via email or other channels as well.
Yeah, that totally makes sense. I mean, one thing that I was thinking about actually when we were having this chat with this either customer service representative or AI, we don't know because we probably failed that Turing test. But when we were having this chat, one thing that went through my mind was how when I was, let's say, early in university, I had tons of time, and so I wouldn't mind sort of kind of optimizing these kinds of things. Like, okay, let's figure out the best way to do this. Let's, we could do different things. We could try different things. Like send us one, and if it doesn't work, then we'll send it back. You said, and now, things are just so chaotic right now. There's just so many things going on. We have kids. We have all these other people sort of in the house, and so now it's like, just send me all three things, and we'll just pick the one that works. And so, like, time is much more important. And, and that's an example of where sort of the customer context really matters, because different people have different sort of states of mind when they might be doing the same thing, such as returning a product and trying to get another one.
Yeah, absolutely. Context is so important. So even if you talk to a human, they wouldn't remember what other conversations you've had. They might look it up in their CRM, but normally there isn't time for them to do that. But with an intelligent assistant like we're providing, it's as if you had a dedicated support person on the other side that actually remembers the last conversation you had. And a good example there is, for example, telco companies where you might have problems with your cable or whatever. So you called yesterday and you had a problem, and then, suggested, well, try this, try moving the router and put it in a different position or whatever. So, next day you call in and then it can say, well, did that help? Mm-hmm. And you'll say, no, well, you've already I know you've already tried rebooting it, so we want to ask you to do that again, and so that's the kind of, it's even better than with a human because, iGo or whatever chatbot with a brain that you have will remember the conversations you've had and what you've done and what you've tried and what you've spoken about. And you will know what equipment you have, whether it's been is on the latest version, and it can do tests, automated tests. It can say, hey, let me test the line, and all of that can happen smoothly and efficiently. Whereas I know we've been working with companies like that, and usually these service calls take half an hour, take an hour with a human agent, and it's just like super frustrating, even resetting your password at a bank, it's like insane of what hoops you have to jump through,
Yeah. We had something recently where, the short story was, we kept getting asked for different information, and we were in the car and we were kind of in a hurry. So we had some mixture of the information, but not all of it. And then that caused, some fraud thing to get triggered, which meant that then, they shut down the whole account, and then things got 100 times worse. It would have been much better to just know, you could even through the phone, you could know that, we were calling through the app, through the bank app. So the bank actually could know that we're in the car. They could look at the accelerometer on the phone and say, okay, maybe we shouldn't be asking for documents that this person just wouldn't have in their car right now.
Right.
So let's dive into that from a technical standpoint. This is a really complicated area. This is one of the most interesting areas for me personally, is this idea of knowledge representation, right? And so, what we've seen over the years are sort of two distinct approaches, both kind of evolving separately, in my opinion, separately, and people constantly trying to sort of harmonize them, but I haven't seen anything. And these two representations are, the symbolic representation. So imagine, expert systems like OpenPsych, what was it called? The knowledge graph at Google, DBpedia. So all of these sort of graphical structures for knowledge. And you can use statistical methods to sort of generate these structures, but at the end of the day, what you're left with is kind of this sort of structure or database, right? And then on the other end, you have this sort of embedding idea. So if you look at GPT-3 from OpenAI, if you look at BERT or any of these other models, you end up with just layers and layers and layers of embeddings. And so these embeddings are kind of projections into some latent space. And so, I think both of these, are extremely powerful, right? We've seen extraordinary things come out of language translation, for example, where, they feed in a sequence of words in one language. It goes into this huge soup of embeddings, and then a decoder emits words in the other language, and it works remarkably well, amazingly well. But to the point you made earlier, it's very hard to go into that soup and say, what do you know? Like, it's very hard to extract from this embedding, like, oh, this person had an issue with their router earlier. And so it's sort of like once you go into that embedded space, it becomes this kind of black box, right? And so I noticed on the, on igo.ai, they talk a lot about, deep learning and the challenges there. And I totally, can level with that. I think that you end up with this system that's very expressive, but not very interpretable. And so what are your thoughts on that whole dynamic?
So there's quite a lot to unpack there. It really depends on the application that you have, how useful, let me call them statistical models are. And for sort of a simple stimulus response type thing, like a search or FAQ or, something like that, that can be very powerful if you have the right training data and, it's tagged correctly and so on. So that can be, just it's the right tool for that. But there are some really fundamental limitations of statistical methods, certainly the way they're employed right now. And one of the key ones I can highlight is that it cannot learn interactively in real time. You basically train the model at the factory, as it were, and then you deploy it. But when you deploy it, it's read only, and that's just, it's a death blow for any intelligent conversation that you have. If you had a personal assistant, if you're talking to another human and you said something and the next sentence there'd be no recognition of what they've said, or it would just be some garbled kind of thing. I mean, let's take something that is trivial for a 5-year-old child. If I say just 5 words, 6 words, my sister's cat Spock is pregnant. So a 5-year-old child wouldn't immediately know, okay, Peter is speaking. I have a sister. A sister has a cat. The cat's name is Spock. You might think it's male from the name, and then you hear it's pregnant. I know it's female. So that information is immediately available, to a human, and to any intelligent conversational AI, it should be as well. So the next sentence might be, she's really big. Okay, well, the cat's big because she's pregnant. Or you might ask, when will the kittens arrive? And that sort of thing is just impossible, and it's trivial. I mean, it's trivial from a human point of view, what you expect in a conversation, to remember and not statistically, but to actually integrate what you hear, to immediately integrate into your knowledge base, knowledge graph, that information. And with statistical systems, they cannot even learn. Certainly the bulk of the ones that are out there, they simply cannot learn. Do one-shot learning, interactive learning, in real time. So you're dead in the water, basically, from that. But even if they could, they would need a reasoning engine as well to say, okay, where does that knowledge that I've just heard actually fit into my knowledge graph?
Right.
And of course, them being a black box, I mean, it's like impossible to know how you would even, where you would put that in your network. It's like an impossible task to do that. Yep. So it's really a complete dead end for having intelligent conversations. You really do need a knowledge graph that is not opaque, and that you have a reasoning engine, that you can have one-shot learning. And I mean, we see the same limitations in image learning, even. Not that it's not an area we're focusing on now, but again, a child can learn a giraffe by seeing one picture of a giraffe. And it will be able to recognize toy giraffes, pink giraffes, and baby giraffes, and so on. No problem with one picture. With deep learning, you need hundreds or thousands of examples, and even then, it can easily be fooled. So there's something just fundamentally wrong with or limiting using big data statistical approaches that don't have one-shot learning, that don't have reasoning involved.
Yeah, it makes sense. Just if I could interject for a moment,
Sure,
just explain to the audience what one-shot learning is. It's this idea where, imagine sort of a competition where you can bring, any machine learning model you want, and you could have done anything to this model. You could have trained it on every image in Google. You could do whatever you want, but the catch is when you go to this competition, they're going to show you, let's say, 5 pictures of animals and tell you what those animals are. And they're all going to be different. Say giraffe, cat, mouse, dog, right? And then that's it. So you're going to have to disambiguate, a ton of giraffes, cats, mice, and dogs from each other just from seeing one example. And so I don't know too much about this area either. I'm not a computer vision person, but I did see some work from Fei Li at Stanford on this, one-shot or few-shot learning. And I think what they do is as I suggested earlier, they train this giant model that tries to understand sort of the core essence and structure of everything that could be seen in the universe. I mean, I don't really, it's hard to wrap my head around that, but they take this sort of soup approach, right? And again, I think it might work in terms of the one-shot learning for image might be doable, but then again, there's zero interpretability.
Right. Yeah, and even you get zero-shot learning, which basically means you figure things out, you learn new things just by thinking about it, basically by cognitive processes, like sort of essentially inference. You have a number of pieces of information, and then from that you synthesize them, and you actually come up with some new piece of information. And that's also related to automatic concept formation, being able to see a few examples of something. I've never seen a trike before or something, and then you see something with 3 wheels, and you have just very few examples, and you can form this new concept. You may have seen bicycles before and cars and whatever, and you can form that concept very quickly. Somebody could even explain it to you that you've never seen one before. You've never seen a trike before. Somebody says, yeah, it's something like a bicycle or motorcycle, but it has two wheels at the back or at the front or whatever the case may be. So yeah. Now, of course, the other side of things, and actually, interestingly, DARPA a few years ago started giving some presentations that they talk about the third wave of AI. So that basically there are three waves of AI. And we find that quite a useful model. And the first wave of AI is what people call good old-fashioned AI, which is basically all the stuff that was done for decades in AI. That would include, Deep Blue, basically being the world champion chess game. It's basically, centered around expert system, formal logic, and things of that nature. And, a lot of AI was basically done that way, narrow AI. And that's the first wave. And the second wave hit us like a tsunami about 8-9 years ago when people finally figured out how they could use neural networks in a, very, very impressive way, partially down to just the massive amounts of data that large companies had accumulated that they never had before, and a massive amount of computing power. So, two of the ingredients that were missing before is having that massive amount of data and computing power, and then a few tweaks to the algorithms, and that really is what brought us the revolution of deep learning, the specialized field of machine learning. And that's been a real revolution, and that is the second wave of AI according to DARPA. But the third wave is basically what we would call cognitive architectures or cognitive. I can't call it cognitive computing because IBM stole that term and messed it up.
Yeah, that's right.
But it's basically having cognition. It's being able to learn and reason, which interestingly enough is sort of full circle going back to the original ideal of AI when the term was coined 60 odd years ago. That's what people were trying to build, is thinking machines that can think and learn and reason the way humans do. And that's sort of the third wave of AI that DARPA identified these requirements that you can basically learn interactively, use context, dynamic context as it changes, and learn and reason interactively.
Yeah, I think one thing that'd be really useful is explaining the difference between what you've just described and just online learning, right? So you could have a deep learning system that is at serving time, it's batching serving requests up into mini batches, and there's some loss there, and so the model is updating in real time. But it sounds like that's not that's not sufficient to cover the kind of adaptability you're talking about.
No, I mean, the model updating in real time, I mean, it's really you're building a new model. There's obviously, whatever I say, whenever you talk about limitations of machine learning, deep learning, there are obviously examples where people are working on overcoming those limits. So, there's a paper here and an experimental system there and so on. So, you can't say it can't be done. Yes, there's probably some one-shot learning. But there really isn't truly incremental real-time learning. I don't know of any system that could do that because, you already called it as batching up. So you're already putting things into bucket. It becomes a statistical soup. My sister's cat Spock is going to get lost there,
that's right.
In that training model. And it has to happen not just in batches, but in real time. I mean, just the conversation we're having now, or any conversation you have, we may not remember everything that the other person said, but generally the conversation has a trajectory based on what was said, what we think, what the objective is, and so on. So the model needs to be updated instantaneously with everything that you hear. And if you can't make sense of it, so, if you, let's say my sister's cat Spock is pregnant and the child didn't know what pregnant was, the child might stop and say, what is that? because
Yeah, right.
it couldn't integrate that, So we have an example on our website, for example, where we have our own sort of version of Alexa, basically the brain behind it, and we say put guac on my shopping list, and then Igo says, well, what is guac? I don't know what guac is, guac's the same as guacamole. So it's although the system needs to be smart enough to know what it doesn't know, and to then be able to automatically disambiguate, and not some hard-coded thing when you say, call Bob, and it says, do you mean Bob this, Bob that, from your list, because somebody hard-coded it. But it needs to be an inherent cognitive capability that when the system gets input and it doesn't know how to interpret that, it basically doesn't understand it, or there's an ambiguity, it needs to deal with it there and then. Like we have to in a conversation. If you have an important conversation, I mean, sometimes we'll gloss over it and we don't understand what the person's saying. Well, okay, fine, we'll move on. But
Yeah,
if you really wanted to, have a useful conversation, you better understand what the person actually says and what they mean. And if it's ambiguous or you don't understand the term, you really need to sort that out there and then. So in that sense, the good old-fashioned approach of having a knowledge graph, an ontology that gets updated, having a reasoning engine, sort of cognitive architectures are in that sense the right approach. But of course, we also know the limitations of good old-fashioned AI, of expert systems. And that's really why we need a third wave. It's the brittleness primarily of formal logic that's really the killer there.
Yeah, that makes sense. So there's a lot to unpack there. I think, actually, well, let's kind of work backwards. So the last thing you said, the brittleness, I think that, that seems to be one of the big issues is with the statistical models, what you get is sort of this integration over millions of different experiences or millions of different documents. So if you imagine, so just some context, the way Google image search at least used to work is they would look at images and they would look at words on the same web page, and they would say these things are weakly connected. And if you have enough web pages, that weak connection can get stronger and stronger. And so, you might have a dog on a page about cats, or just some random page about astronauts or something. But chances are you have a lot more dogs on pages where you have the word dog and the word canine and things like that. And so versus, in the expert systems, at least the first wave, let's say expert systems, they were brittle in the sense that they couldn't, at least, in my opinion, they couldn't handle mixtures very well, because a combination of it causes this combinatoric explosion in the different possibilities, and also because there's a lot of sort of human in the loop. I think for OpenSlake, a lot of that is written by people. I know some DBpedia and some of these other ones have been kind of scraped off the internet, and but there's a lot of hand engineering there. And so how do you think we're going to sort of overcome that, and maybe sort of, I guess, take the best of these sort of symbolic systems that have been traditionally curated by hand, and like WordNet comes to mind, right? And some of these statistical methods where you're using a lot of electricity, but you're not using a lot of human effort, right?
Right, right. So I believe the answer lies in what DARPA calls the third wave, and one way to describe it is as a cognitive architecture. So you basically start off by asking yourself, what is intelligence? What does intelligence entail? And, you can kind of make a practical laundry list of things. And, we've already spoken about some of the key ones is to be able to learn interactively, to be able to deeply understand and know when you're not understanding stuff. And to be able to reason about things. So those are, maybe three key things. And your architecture needs to inherently be designed to be able to cope with that. Now, some of the cognitive architectures have been around for a few decades, and they haven't really worked that well. But primarily, the reason they haven't worked well, and I just want to interject here, neural nets, also for decades, people worked on it, and you could say, well, neural nets don't really work,
Yep.
They don't work until they do,
Yeah, exactly.
until somebody figures out how to get them to work. And I believe that's sort of where we are with cognitive architectures. People have tried to get them to work, and they haven't worked for reasons which I believe we understand quite well. One of the things is they are based on formal logic. Most of them are based, or pretty much all of them are based on formal logic. And formal logic, like the problem that Psych had, can't handle contradictory information. So, what Psych ended up doing, having microdomains where within the microdomain, it had to be consistent, but the domains themselves didn't necessarily have to be consistent. That's sort of roughly how they dealt with that. But that's not nearly fine-grained enough. You can read that Google bought DeepMind for 400 million, and another article, Google bought DeepMind for 600 million. And you say, well, and your system really just needs to be able to take them in stride as we can. Okay, well, there's something not resolved until you find out the one was a newspaper report from the UK and the other one from the US. So the one was in pounds and the other one was in dollars.
Yeah.
But you can, in the meantime, you need to basically capture that knowledge, and a formal logic system would just fall apart. If it had this contradictory information, you have fuzzy information. Some guy is a short basketball player, hey, the poor guy's only 6'5" or something,
Yeah, right.
So he's a short person, So being able to contextualize what, the meaning of things, that those kind of things. So formal logic hasn't been able to deal with that. So the answer lies in basically having a knowledge representation and a logic engine, a reasoning engine that can inherently deal with contradictions, with fuzziness, in an effective way. So I think that's really the way to go. Now, the question you asked about not having a human in the loop to get the knowledge, this is really, really tricky. We as humans just pick up such an enormous amount of common sense knowledge. Even a 2-year-old has it about how the world works. And to get that knowledge represented properly in an AI is really, really hard. And especially if you don't have embodiment, if it's not actually a robot that crawls around or walks around in the real world and learns. But
do you feel like it's genetic? Do you think that a lot of this information is multi-generational and it's encoded in that way? Or do you think that we are able to really kind of bootstrap? Because the 2-year-old thing blows my mind, or even just a baby is able to have so much common sense reasoning. I don't have any data, but just like intuitively, it feels like there's got to be some kind of genetic stamp there.
Yeah, I think there is, and that's it's kind of a very difficult thing to unpack. Basically, nature versus nurture, so we're clearly not a blank slate. Babies are not a blank slate. That's for sure. But is there, are we born with knowledge? I don't think there's evidence that we are born with knowledge per se, but again, it's very tricky. Where do you draw the line of what you call knowledge? I mean, a baby knows where it's going to get fed, or what it needs to do to get milk. So it has those instincts, that are obviously in DNA as they are for animals. But I think the biggest part is, so yes, there are some built-in instincts that allow us to survive and bootstrap ourselves. But I think the bigger thing is sort of built-in feature extraction. And I think the very good example, a very obvious example there is, in our visual system that we basically clearly have feature extraction for, lines, for vertical, horizontal lines. If we didn't have that, we'd have a much, much harder time being able to, recognize objects and to basically to get a visual system to be effective. I'm not an expert on what all the feature extractors are, but clearly there's, there are hard-coded feature extraction that helps to get us going. So from an AI point of view, to get back to that, it'll be a combination of having to kind of hard code, preload the system with enough information to bootstrap itself. And that's kind of one of the things we're doing in our company. I've been working on the project now for more than 20 years. And, the approach we use, we call artificial general intelligence as opposed to narrow AI. I actually coined the term AGI together with two other people in 2001 to make that distinction that narrow AI is really not what we're after. Narrow AI, you take the intelligence that the human has. We were talking about human in the loop. You take the intelligence that the human has, and you're turning that into code, or you take the intelligence, the insights that the human has to help you build a model that you can then deploy. But it's really the human intelligence that's being turned into code or model. The intelligence doesn't reside in the code or in the model to, at least not to a significant extent. So artificial general intelligence is all about building systems that can learn more and more by themselves. But you need a certain level of bootstrapping that basically the system can hit the books, as it were, and hit Wikipedia and actually have enough of background understanding to make sense of what it's actually reading,
Yeah, I mean, I think in the in the deep reinforcement learning, or let's say reinforcement learning community, there's world building models, there's sim to real, right? So in this case, there's examples where you say, given the current state of, let's say, my robot, I'm going to predict if I take this action, what the next state's going to look like. And so I'm going to build this state-to-state function, right? And then there's even embed to control, where I'm going to say, okay, the state is kind of difficult to output because maybe it's some sparse state, maybe it's a graph or something like that. I'm going to embed this state in this latent space. And in this latent space, I can have simulators, I can hallucinate in this latent space, all these alternatives, right? And so people are trying to do that, that sort of sim to real idea. But again, it's this soup, right? I mean, what you're left with is this really odd, embedding of, let's say, Pac-Man and the Pac-Man universe, and it's completely uninterpretable. And it's whether it adapts or not is unknown. I mean, you can't know that in advance, and you can't extract, a knowledge graph or anything meaningful from it. At least not directly, right? And so, yeah, I guess, how does the cognitive architecture allow you to sort of build upon, allow it to be sort of aglometric and continue to build on itself?
Right.
Without falling back to this embedding soup thing. Right.
So the sort of the key, one of the insights that I got from philosophy, epistemology, theory of knowledge, that is really crucial in understanding, trying to figure out how to build the systems, is the importance of concepts. And that is basically how your knowledge is represented. So deep learning, machine learning systems basically optimize on whatever features they can use, minimal features they can use to categorize something. So, if orange pixels are the thing to categorize it, then so be it. But it may be that all your examples were orange things, and when you come across the green
There's
thing.
The famous Army tank example, right? The Army built a model for this to detect Russian versus U.S. tanks. When they took pictures of the Russian tanks, it was at night. And so the model ended up being a nighttime predictor instead of a Russian tank predictor.
Exactly. That's right. Whereas humans, we extract what are the essential features in a contextual basis, and what we want to form the concept for. And yes, in your example of the tank, yes, the fact that it's day or night is totally irrelevant. So therefore, that's not a feature that we would encode for a tank. And we know that because of the background information that we have and the purpose that, why, this is all subconscious, of course. We know what this concept is supposed to be used for. and that can adapt, that can change over time. You may, as a child, the concept of a dog or a cat may be, hey, it's something to play with and, can bite you or whatever, the case may be. But then you become a vet and suddenly the concept changes very, very dramatically, in terms of, well, what kind of cat is it, what does it look like, and can you detect a particular ailment or whatever. So the concepts themselves can also change and adapt to the use that you want to put the concept to. But the concepts themselves need to represent the key features, the essential features for the purpose that you're trying to put it to. But in addition to it, you also embedded in that, you have the concrete examples. So you can fall back on the concrete examples. When for example, we don't have photographic memory, but certain things we do remember well. So, if that first picture of a giraffe really made a big impact on a child, then it can probably recall that picture. It'll still have the example, and yet at the same time, it'll have a representation of a giraffe that has extracted the essential features. The long neck, the long legs. That's the essential feature that makes it obviously different from other animals. It's an animal, but what is different? One elephant with a big trunk and big ears. Those are really the key features.
Yeah, that makes sense. And so the way you figure out it's the frame problem, right? So you look at a giraffe and there's a million things you could say about this giraffe, but until you look at a bunch of other animals, it's hard to know what separates this giraffe from the other animals. Like if you're in the savannah, you might start by saying, oh, well, giraffes are yellow, but then you find that lions are more or less yellow, or I guess brown. And tigers or not tigers, lionesses are brown, maybe warthogs are brown. And so, okay, maybe you say, okay, color is maybe not the defining characteristic of the giraffe, right? And so how I imagine this, and I'm definitely not an expert in the cognitive architecture, although I want to be after hearing the talk so far. It sounds really exciting, but it sounds like you have this sort of this like quantum superposition of all of these things that could be interesting. And over time, you're having to sort of refine that and continue to update that.
Yeah, exactly. I wouldn't put it anywhere as mysterious as, quantum phenomena.
Okay, yeah, right.
But absolutely, you can basically, as you see, also one of the other problems with deep learning statistical systems is they throw away the examples. The instances are not encoded. So whereas in a cognitive architecture, it's cheap and easy, with memory to actually you have a photographic memory and remember the original sentence that you heard the utterance in, or the sentences that you heard. So you have the original instance, or with images, you have the original image. So you could then retrospectively refine or redefine what the essential features are. You might, as you say, the giraffe might be the first yellow animal you see, and so you think maybe yellow is like really key. But as you see other animals, no, that yellow is not a distinguishing feature. And then you see toy animals, which could be purple, or purple unicorns or whatever, or pink unicorns,
right.
Pink elephants. You say, well, yeah, actually, you have that sub-concept of, anyway, you have that overlapping concept of toys, which, automatically have some different kind of weird features that can modify the other features. They can be a completely different size, they're much smaller, they're soft, they don't bite you, and they can be a weird color,
Mm-hmm.
But you can still tell a giraffe from an elephant, a toy elephant, by just extracting, using different features within that context.
Yeah, that makes sense. So one thing, a lot of these systems you're building, you have to have conversations or are designed to have conversations with real people. And so humans have set up kind of our own vocabulary or our own sort of common sense reasoning. And that might not be optimal or even close to it, but it's sort of, it is what it is. If you want to talk to a human, you're going to have to use the sort of common sense atoms that a human would use, right? And so how do you sort of reconcile that? I imagine if you really started from scratch, saying we're going to build this kind of knowledge graph, then it's going to say, oh, giraffes have a bend in their ear and other animals don't. But no person would ever think about a giraffe in that way, right? How do you deal with that disconnect?
Right. It's a very interesting question, because when I started on the project, initially we were in pure R&D mode. We basically took the ideas that I'd come up with of cognitive architecture and built various prototypes. So we had a virtual mouse living in a virtual environment and learning, it had, virtual ears and nose and whiskers and so on, and to learn in the environment. And we then had different prototypes with different animals, dog, and then we had child, and we tried that. And then we decided we would focus on natural language, but at adult level, basically. And so we spent several years teaching the system a whole lot of different things that we thought it should know, the kind of background knowledge that it should know. But then when we commercialize, when you try to now use the system in a real life situation that is going to do a job, a useful job, you actually in a way have to dumb down the system.
Yeah.
But it's actually not that different from you might be offshoring your call center operations, and you don't want the person in wherever they are in India or Philippines or whatever say, hey, I know how to sell this product much better than my boss told me to do, and I'll go off script and just do that. No, you want the person to stay on script. That's what the company has learned. So we need to basically constrain IGO to stay on script, as it were, and to say things that people would expect, and to listen for things that we would expect people to say at that time, and not try and learn new things, and form new concepts. So in that sense, you're kind of dumbing the system down for that. So the kind of research path to give it true open intelligence and the commercial practicalities, do tend to diverge, and that's one of the challenges I've had since commercializing it, is to make sure we can still continue cranking up the IQ and make the system more and more intelligent, but without it going off script, so to speak, without it trying to be too clever and obviously not clever enough. So that's kind of one of the challenges, and I actually call it the AGI trap. That to build a commercial system, it's almost always easier to hard code things and to do them in a narrow AI way than to try and do them in a sort of really cognitive architecture way. And so we need to strike that balance. So yeah, you pointed on a very important issue there, that general intelligence at a baby level is not that useful.
Yeah, right. And I think that actually, you could extrapolate that to a lot of different domains. And let's look at robotics, for example. A robot, people are so worried about robots taking over jobs, but it's not just that the robot has to be able to do the job, but it has to be able to be more efficient than a person. I mean, if you have a robot, but it's going to require I don't know, $20 an hour worth of, maintenance, and maybe it fails every now and then. And well, then, and if it's doing a job that you could have someone do for $15 an hour, then that's no good, right? And so I think you can find almost any domain where what you said is true. I mean, even if you look at video games, so video game AI, you could spend a ton of time. My PhD was on playing various games, and you could spend a ton of time making a really complicated video game opponent. But at the end of the day, the goal of a game is to be fun and to sort of keep people in the zone. And so it's much easier to do that by having a knob. It's like if the person's doing too well, then you just crank up the knob, and there's just more of the same dumb enemies show up next time.
Right. Yeah. No, it's. The way we're thinking about it is to. Our goal is to get closer and closer to human level capabilities, because I believe it's going to be enormously beneficial to humanity to have that. And we sort of bootstrapping it through kind of a skeleton where the system, we hard code, or we're not hard code, we don't code it, but we teach the system sort of rough common sense knowledge in an ontology. But we know that knowledge is not the way it should be represented, but it's kind of just to help it bootstrap. So think of it as like a scaffolding that the system should then build its real knowledge around the scaffolding, and eventually the scaffolding itself just dissolves because it now has, it's acquired the knowledge in a way that it really should have acquired it in the first place. So that's kind of how we see the bootstrapping process to higher and higher levels of intelligence. But it's hard.
Yeah, I mean, that makes sense. I mean, I think you see this in the real world. I mean, in with real human beings, and you see this in industry settings as well, where in the real world, you don't let your child put his hand on the stove, right? Like you don't let them learn that the hard way, right? Or stick a fork in a socket or something. Right. So what that means is that they're not going to fully understand what it means to sort of put your hand on the stove until they're older and they understand heat and what heat could do to things and so on and so forth. But the alternative is someone gets seriously hurt. So you kind of have to sort of bias someone's knowledge, right? And what you see in industry sort of decision-making systems is something similar where, like, for example, if you were to build a system to decide how many ads to show on a Google landing page, right? It might want to try to fill the whole page full of ads, right? Because that could be interesting. But that would kind of hurt your brand, right? And so you kind of have to start with, something that's very focused, very guided, and then allow kind of a little bit of creativity. And then, as you said, eventually, as the system starts to learn and reason, especially starts to reason counterfactually and starts to be able to understand, if I filled the page full of ads, no one would come back, right? If it can reason that from limited set of experiences, then you can sort of, take the training wheels off.
Right. Yeah, absolutely. Those guardrails need to be there. But it's having an architecture, having an approach that inherently allows you to increase the level of intelligence and to, that has the features that are needed for intelligence.
Yeah. So one last sort of technical question, and we should definitely jump into IGO as a company, as a product, and as a place to work. So, how do you sort of? It sounds like the cognitive architecture it's an evolution, but it's also kind of a unification of the past, right? You have these knowledge graphs, these sort of symbolic systems. You have the sort of primordial embedding soups, and this is sort of taking kind of the best of all of that, where you're using statistics and reasoning and things that you've observed to sort of have this living knowledge graph. And then the part that I wasn't totally clear about yet is, are you also then using the expert systems approach, like using search and IR methods on that graph that you're updating in real time? Is that part of it?
Yeah, I mean, from a practical point of view, and that could be, other people may have a sort of what should I call it? A cleaner theoretical approach than we have. I'm as much a businessman as I am a scientist or researcher, and so to me, I look at it as an engineering thing. Is what's the best way of getting it done? What's the best piece of technology or algorithm or whatever I can use to get a particular component to operate efficiently. Now, if you took a theoretically cleaner approach, you might say, well, no, we can't use a brute force approach, because the brain doesn't do it, or it shouldn't really be using it, or because ultimately not going to be scalable or whatever. So I'm less concerned about that, and we'll use search for some of our algorithms. So we'll use whatever tricks in the book. This is hard enough. We don't want to say that because this is not theoretically as clean as you might like to have it. We've got to get it to work. So we'll use whatever we need. But the core foundation that we found is really having a knowledge graph and having the right knowledge representation that has the flexibility to deal with contradictions and with fuzziness, with and context and so on. And that knowledge graph has to be super high performance. I'll talk a little bit about why cognitive architectures haven't worked up to now. And I can mention three reasons for it. One of them is the brittleness of good old-fashioned AI, of formal logic. Most of them tried to get away with formal logic, and they just hit a wall on that. The second thing that we're finding, we've spoken to quite a few labs that are trying to do conversational AI and to use knowledge graphs interactively in the conversation, to basically get context and to update the knowledge graph and to basically use it interactively in real time. And they found they hit severe performance issues. So we developed a knowledge graph technology that's 2 orders of magnitude faster than any commercially available graph database, 100 times faster.
Wow.
And that makes all the difference. That basically, where you could have a sub-second response to something that somebody says, versus having a 500 50-second response, a minute response, which clearly is unacceptable. Because we might hit that knowledge graph hundreds of times or thousands of times while we're trying to make sense of an utterance. So those are two reasons that the performance of the knowledge graph and not being constrained by formal logic approaches, those are two reasons. But the third one is actually more an accident of history, and that is that nobody's working on cognitive architectures. And why is that? Well, primarily because deep learning has been so incredibly successful in so many areas. So it's sucked all of the oxygen out of the air.
I remember when I was studying deep learning, it was in the deep learning winter. So I got my PhD in 2009, and you actually couldn't publish a paper in deep learning. You couldn't submit a deep learning paper to NIPS. They would reject it. It'd have to be truly remarkable to get into NIPS.
Wow.
And now all of NIPS, is just neural networks applied to everything. And to your point, I think that's the goal of an academic, or in this case, like a company that's really forward thinking, is to do that thing that nobody else is doing. So I think that's pretty cool.
Yeah, and we had, as a concrete example, we had a brilliant intern from Germany working on our project quite a few years ago, and he really got the cognitive architecture concept, and he had, and understood the thing. He was with us for a year, went back to Germany to do his PhD on that. He couldn't get a sponsor. He ended up doing a PhD in deep learning.
Yeah.
You want to earn the big bucks. You want to get your paper published. You want to, get a PhD. You want to get funding for your company. Deep learning is the only game in town. So all of the big decision makers at the big companies and the VC firms and that, they're obviously all deep learning. That's the only game in town. So that's actually, quite frankly, one of the big reasons I believe that cognitive architectures haven't made much more progress. And I've just been blinkered. I spent 5 years doing my own research before I started on this project to really deeply understand what intelligence entails. How does our intelligence differ from animals? How do children learn? What do IQ tests measure? Are they meaningful? I studied epistemology, theory of knowledge, and even what is reality? What is our relationship of our knowledge and certainty to reality? And really deeply understanding cognition from all these different angles, from cognitive psychology and of course the different fields of AI, and then I came to conclusion. Okay, we need what I now call a cognitive architecture, and it's just been so obvious to me that that's required. There's no shortcut. That it has to learn interactively in real time, one shot. That's not negotiable.
Mm-hmm. Yeah.
And if you're working on any system, if you're not solving that problem, you're not going to get an intelligent system. It's as simple as that, So sort of a generally intelligent system, and a few other things like that. And this is why I've been blinkered working on this with limited budget, I was fortunate enough to have a good commercial success with a software company I formed, did an IPO on that. So that gave me enough time and money when I exited that company to actually embark on this project. And I've been able to fund it, with about a dozen people doing research. And then we commercialized the first generation. And now for the last 6 years, we've been working on the second generation on iGo AI. And but it's you really have to be certain that this is the path. Like some of the pioneers of deep learning were sure that deep learning or neural nets of some sort were really, really powerful and useful eventually, and they turned out to be right.
Yeah, I mean, one of the things I've been talking a lot about at work for years, and we haven't really been able to make progress, is this idea of, if you have an embedding, recovering like an English explanation of that embedding. So imagine if you have an embedding of all of a person's activity on Amazon, could you write a bio about that person, right? Like, could you just take that embedding and output, emit a bio, this is Bob loves soccer products, and Bob buys things in the evening, right? And again, of course, you could do it with a lot of human engineering, but the thought experiment here is could we just organically, go backwards? Like, you can clearly, there are encoders that can clearly embed English and translate it into French. We've seen that. But could you do more? Could you encode experiences and translate them into English, right? And I think that is something that's proving to be extremely difficult. And I think what we're starting to realize is, maybe something you've realized for a long time, which is that, symbolic representations, they're not things that can be just emitted from embeddings. And these are things that have to kind of work together in harmony.
Yeah. Well, I mean, the example you're giving is actually a very, very powerful one. Is could you do it? And I think the way statistical systems are set up, I mean, even the fact that they're statistical immediately negates that possibility, because you are trying to average out over, many instances of what is the average thing that happens. So you have to lose the original instance information. So therefore, you couldn't reconstruct it. You could only reconstruct the average. And one of the huge failures of or limitations, I shouldn't call it failure because they're not trying to do that, but limitations is you can't deal with the outliers. If my profile says, my personal profile of what I buy or what I do, what my activity, let's just for argument's say it has a 99% confidence that I would be interested in cricket. I lived in South Africa for
oh, okay. Well, there you go.
Or whatever. I drink tea. I love tea. So whatever my profile. Let's just for argument's say. But I don't care for cricket at all. But my profile would suggest that a statistical system can simply not deal with that.
Right. I mean, all of them require regularization to perform. I mean, that was one of the big, one of the hallmarks of deep learning was dropout and was exactly. Batch norm and ways to eliminate outliers.
Right. It's their strengths, but therefore you can then never deal with these outliers of people that are that don't fit the statistic. And this is also one of the reasons why it can inherently not work in an ongoing conversation. I mean, apart from the sort of example I gave that you have to learn in real time, but even putting that apart, setting that apart, if you have a lot of sort of the normal kind of conversation, if a statistical system has an 85% accuracy or something, on what response to give, well, if you have a conversation and you 3 or 4 or 5 sentences into the conversation, you multiply the 85%. You're down to gobbledygook, basically.
Yep. It's not designed to recover either. As you said, it's not designed to ask the pointed questions to. Let's say, hey,
I'm lost here. Explain that to me. So and there's actually kind of one last thing I just like to come back, because you've mentioned a few times the relationship between embeddings and symbolic, and Yeah, so they're the problems of how information is encoded in deep learning systems, that it's not encoded in a conceptual format. But you need to have it in a conceptual format to be able to then link it to the symbols, because the symbol refers to the concept. But the concept itself has to be represented in the right way with the right features, and that's why, it will think that, a stop sign is a fridge or whatever,
Yeah, right. One thing that I saw from Google that really resonated with me was early on in the embeddings. This was maybe 2011. Deep learning was still kind of catching on, and the person, I can't remember their name. Patrick, you would know this. The person who is the MacGyver of Google, totally drawing a blank. There was a whole page. Jeff Dean, thank you. Yeah. So Jeff Dean, came and gave a talk on embeddings, and they actually were trying to draw symbolic inferences from embeddings. So, for example, you could minus king from queen, and you could minus lion from lioness, and you would get the same vector, right? Yeah. And that seems so powerful, but in a way, now in hindsight, we have 10 years of hindsight, that was quite the red herring, wasn't it? Because it really suggested that you had the symbols there, you just had to do some algebra to get them. And here we are 10 years later with almost no progress, right?
Yeah, I'm actually so glad you mentioned that, because I love talking about that exact example, that it was seen as a revolution, and I always called it a parlor trick, because that's exactly the examples I gave. You could take Paris, subtract France, and add England, and you'd get London or whatever.
Yeah, right.
But when this first came out, we actually tried to use, this is word to vector basically.
Right.
Word to vec. We actually tried to use it in our system to see, would it help us bootstrap the system? And we very, very quickly found out that it actually wasn't. Not only wasn't it useful, it was actually counterproductive. And I can give you a simple counter example that in vector space, cats and dogs are much closer together than dog and puppy.
Yeah, probably
because in text you'll find cats and dogs mentioned, and not dogs and puppies, usually in the same sentence. And you very quickly find those kind of limitations. So even it's as I say, it's sort of just a parlor trick. That's wow, yeah.
It seemed amazing. You hit another point, which substitution is devastating to embeddings, because if one word could be substituted for another, you'll rarely see them together, and then that drives them apart. But they're actually the same exact concept.
Right. Yeah, but interesting times we live in, So.
Yeah, I mean, this is super cool. I mean, I definitely, what you said really resonated with me, having been a big proponent of multi-layer perceptrons back when they weren't popular. And I do think that this we do need a stepwise advance. I think we're starting to hit the limit. I mean, GPT-3 is so many gigabytes, right? Every time I see models get really large, it's a sign that, we're starting to run out of low-hanging fruit. And so I'm really excited to see. Yeah, I'll definitely be doing a bunch of reading on this. And I think you have a bunch of posts on Medium with some really good content. So what we'll do is we'll put that in the show notes so that folks can read more about this area.
Great. Yeah, that'll be good. And welcome any questions, feedback on that. I have quite a few articles on Medium.com, including risks of AI and ethics and so on.
Cool. So tell us a little bit about the company. So you told us, it was founded, I think you said 20 years ago, or
my first R&D company was in 2001 that I founded first R&D company. We then launched our first generation commercial product in 2008, a company called Smart Action. Smart Action is now about 100 people or so. And providing an IVR with a brain. But I found that the commercial pressures of providing a SaaS service reliably, with security and redundancy and performance and integration and all of that. That kind of sucked up all of the time and energy. And we really didn't spend any more time on cranking up the IQ because that wasn't sort of the bottleneck in the company. So I exited that company 7 years ago and started Igo.ai so that I could concentrate again on cranking up the IQ. So I hired a new team, 12 people. Have an awesome team now, and we basically for 5-6 years we were just in development mode, not in R&D mode because we'd already done the research, but we knew what needed to be done to basically make the system more intelligent, more capable. And then about a year or so ago, I got to a point where we said, okay, we're now ready to commercialize the second generation. And that's basically what Igo AI. And we just launched late last year officially. And we're now fully in commercial mode. We 16 people right now. We actually aggressively hiring right now. So we hope to be hundreds of people in not too distant future.
Cool. So where's the company located?
We're in Los Angeles.
Okay, cool.
Yeah. And we're exciting times. So it's while I said earlier, the commercial thing sort of pushes you in a different direction from just focusing on artificial general intelligence, IQ. And so working very hard to balance that. But the commercial activity is also a very, very good reality check because you can have all of the theoretical things in the world. You could write papers about it or beat benchmarks or do whatever, Ultimately, the rubber hits the road when you're trying to use it in the real world. So the commercial aspect I find invaluable, but we just need to, from what we learned previously, is we need to make sure that we have enough resources to keep our development team going full speed while we also commercializing and getting that feedback and the money.
Yeah. Oh yeah, totally. Yeah. So do you have two sort of separate branches, like a fundamental research branch, and I guess the company is still smaller, but as it grows,
right now, I mean, the people we have, we're all hired for their, sort of for the development roles, but as we've gone commercial, they've all been very excited to be part of the commercial team. But yes, we'll be separating it more as we move forward, but we don't want to silo them at all. We want to make sure that there's a lot of cross communication for sure.
Yeah. One of the biggest follies I've seen in research labs is where the communication only goes one way. So the idea is you have this fundamental research team, and they're going to write papers, and they're going to email the papers over to the applied. Yahoo is like this. So there's Yahoo Research. They would send the paper to Yahoo Labs, who would then try to fit it into different products. But then no communication went the other way, and so that actually hurt the research team more than anybody because they were just operating kind of in the dark.
Yeah, in a vacuum. Yeah. So we're in a fortunate position that, I'm, as I said, as much of a businessman as I am a cognitive scientist or AI scientist. So I'm really super excited about both aspects. And, so being able to guide that from the top, that to make sure they don't get siloed is will definitely help us.
Yeah, totally. So so if there's folks right now, in university, are you hiring? What kind of roles in general are you looking for? Do you have internships?
Yeah, so we have had interns in the past as well. So potentially, of course, it's a little tricky right now because doing interns without physical presence is hard. So we don't know yet how that's going to pan out. But the interesting thing in our company is which is very unusual. 70% of our staff are what I call AI psychologists. It's actually a profession I invented. But they're basically either linguists. They either have linguistics training or cognitive psychology training. They're not programmers. And this is again because in our cognitive architecture, a lot of the work is being done through training Igo, not programming Igo. So, giving it a curriculum, building the ontologies, teaching and having tasks. And then 1/3 is basically engineering, where we do the actual coding and integration and so on.
Yeah, that makes sense.
Yeah, and typically I actually prefer to and this is a generalization. It's not a not
sure.
That's what I do is I generally actually prefer people who don't have a lot of AI experience, because otherwise there's too much to unlearn.
Yeah, right. Yep. Yeah, everything will be framed around how do we, what's the loss function, what's the embedding? I mean, you just get asked that every day.
Yeah, exactly. So we're really just looking for people that are smart and motivated and that are particularly excited and working on this kind of project, that don't want to work on some ad optimization algorithm or whatever, or Uber for dog food or whatever.
Yeah, Uber for dog. So I think the so can you kind of walk through what the job? I mean, actually, what you said really resonates with me. This idea of training the AI. So someone who, I mean, clearly there's different roles. There's DevOps. There's people who are optimizing the database, and so those roles are pretty well defined. I think most people who've been following the show know what that's going to be like. But tell me more about the training. I mean, so this AI psychologist, you said?
Yeah, AI psychologist.
Yeah. So what is that person? What is a day like? A typical day like for that person?
Yeah. So there are quite a lot of different sort of specialities within that, but they all kind of revolve around analyzing different kinds of conversational scenarios. So, I mean, on the commercial side, before we were commercial, we would make up our own scenarios, like, my sister's cat Spock is pregnant, and being able to understand that. Now it's more like, I'd like to change the delivery address on my order, that.
Yeah.
Or I'm having trouble with my internet service. So it's basically being able to parse the sentences that we get, and to be able to parse them deeply, to handle disambiguation, to handle ambiguities, hopefully automatically through context, basically saying, okay, here's something ambiguous, but do I have the context that can disambiguate that? And then basically, does the system already have the knowledge and the algorithms to do the disambiguation effectively? And that disambiguation could also be done through reasoning. It could be, send an email to Bob. Now you might say, okay, I know 2 different Bobs. The context may not tell me, but there may be other things that you can reason about. Say, well, it can't possibly be that Bob because whatever, he died.
Yeah,
whatever,
right.
Yeah. So there could be reasoning or context or something. So disambiguation, deep understanding. One of my articles is understanding. There's actually, it's a very interesting topic, just what understanding entails. So a lot of the work we do is in deep understanding of what the person is saying, but then on the other action side of things is, okay, how do you respond to it? There's natural language generation, and or doing certain skills, doing certain tasks, which may entail subtasks. Does the system know how to do those subtasks? Do we need to teach it? Does it need to gather more information to do it? So, for example, if you say, I want to change the delivery address on my order, well, then it can do that task, but only if it knows what the new delivery address is. So it automatically, without us having to program it, it should know that here, there's a piece of information that's missing to do this task. I need to ask, well, what would you like to change the address to? So it's basically working through that and making sure that IGO has the right knowledge, and then highlighting fundamental cognitive deficiencies, where we say, hey, IGO should already be able to figure that out itself. But the cognitive mechanisms aren't strong enough, and then we sit down and figure out, okay, how can we make it smarter, so that next time we don't even have to teach it that. It can basically already figure it out itself or ask for the information. So that's kind of the iterative process. And yeah, it's super interesting stuff.
Yeah, that makes sense. I mean, a lot of what you said reminded me of active learning, right? Where you're kind of looking for, and I guess I'm doing the thing that I shouldn't be doing. I'm going back to loss functions and all of that. But it's sort of like you sort of look for things that are on the hyperplane, or in this case, you look for things where the system's entirely ambiguous, and you try to sort of tease apart those examples explicitly.
Right. Exactly. Yeah.
Cool. Wow, that's totally wild. So the team right now is kind of centralized in this office in LA, and is there any plans to grow? So if someone is, are all the positions you're hiring for in LA, or are there any remote opportunities?
Yeah, right now there are. We haven't yet figured out how to effectively interact and manage remote people, but I'm sure we will. We just need a bit more management structure and so on. So yeah, right now we have everyone in Los Angeles.
Cool.
But that'll change hopefully in the near future.
Yeah, that makes sense. Cool. And so if people have questions or they want to write you about different, career. I'm sure there's a careers page on igo.ai, so people check that out first. But if they have anything they wanted to chat to you about, how can they reach you?
Yeah, medium.com they can always respond there. But I'm also easy to find on Facebook. I'm on Twitter. Peter Voss. I think you'll be able to find me quite easily.
Cool. Great. Thank you so much. This was an absolutely fascinating talk. I definitely have a lot of research to do, and I'm sure the listeners out there have a lot to do. There's a lot to unpack, but we have a really motivated community, and so I think that I think you really kickstarted them into the next year. So I appreciate it.
Great. Well, this was fun. I enjoyed the conversation.
Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix and adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.